impairments that you can easily identify what the impairment is, what some of the likely causes are, and eliminate some of the red herrings or the artifacts that aren't actually present. Now, the other thing we need to know is there's a power relationship between how the DOCSIS devices themselves measure power on both the downstream and the upstream side in composite power across a portion of the spectrum versus the mathematical representation that we see on these spectrum analyzer tools. So for instance, we're looking at the same device in two different ways. This is a Comcast tool called Scout, and it's telling us that the downstream receive power of that device is right around 0, plus or minus a half. Now, when we look at the visual representation of that tool, it actually shows on the vertical axis that the power is negative 17. So what's the actual received power at the device? Is it 0 or is it negative 17? It's actually 0. So when you're looking at some of these screenshots, what you need to do is to look at the amplitude or the vertical reference level and then add 17 to it to get the actual power at the device. Now, some tools could be slightly different. It's a logarithmic equation that determines the delta there. Some other tools are 18, some could be 15, but most of them are somewhere around 17 dB delta. Okay, so let's start talking about the different types of impairments that tools like this can help us define. The first one we'll talk about is an adjacent channel alignment. So there are several different examples of this. You can see here in the low portion of the spectrum here, right around 107 megahertz, there's a channel that's just sticking out. A lot of times we see that with local insertions. You have an apartment complex or an MDU, and they want to look at their parking lot or their front door cameras or whatever, so they'll have a digital insertion with a modulated channel from their cameras and then insert it into our lineup. If that power isn't matched to the insertion point power at the combiner, then you'll have that adjacent channel alignment. So that's a quick indicator that, hey, if all of the modems in this apartment complex or MDU have this one channel sticking out, but the neighbors outside of there don't, well, it's a local insertion issue. Now, other times, you'll see things like this. So the bottom half of the spectrum is the linear broadcast or video channels, and then you get into your DOCSIS channels or your narrowcast channels, and that's typically a product of combining in the head end. So if you see that in the house, there's typically nothing you can do to fix that in the house, right, or in an amplifier. You can't go out and adjust your narrowcast versus your broadcast. That's typically a head end function. Very similar with these other two examples. We'll have a portion of the spectrum. It could be 4 channels, it could be 8 channels, but then adjacent to that, there's a significant difference in the power levels. In a lot of cases, that's in the head end. Okay, standing waves. Now these are what we call simple or periodic standing waves caused by impedance mismatches. So just like Brady talked about those impedance mismatches and the reflection of energy back and forth inside of a reflective cavity, the similar thing happens in the downstream as happens in the upstream. However, it's represented differently in the downstream because we have much more spectrum that seems connected than in the upstream where it's smaller channel frequency responses that are disconnected. Now, there is a formula where you can take and measure, and I bring this up because I mentioned the deck that John Downey shared with me in 1990 something. In that deck was the formula for how to measure the peak-to-peak distance in megahertz and determine how big the reflective cavity was. So it was a way of calculating cavity size, reflective cavity size, before we had the intelligence tools to do it. So you just had to measure the peak to peak of your standing wave at a point and then do the math at the difference in frequency from the peak to peak or null to null And you could determine how far you were from the reflection. Looks like somebody's talking in chat here. Let's see who that was. Oh, thank you, John. The reference power is based on the resolution bandwidth, John says, going back to the previous slides. And to have a 17 dB correction factor, the cable must be using a resolution bandwidth of 100 kilohertz. Thank you, John. So if we go back to that slide, this one, he's exactly right about the resolution bandwidth and measurements. Now, that's not captured in this deck, but I will tell you in the PNM paper that we referred to, there is a lot of material in here about how these visuals are constructed. And thank you, John, for keeping me honest. I'm going to fast forward down here to a part of this paper that I did not include in this deck that speaks to, here you go, the visualization and how it's measured with resolution bandwidths of different bandwidths. So 100 kilohertz, 10 kilohertz, 100 hertz. So the visualization of the spectrum is influenced by the resolution bandwidth measurement. And John, ours is about 117, so it comes out to 17.17 or so to get that 17 dB correction. Now that's included in this paper that the Working Group 7 put together, and is very, very comprehensive. There's a lot of information here about the differences between different types of analyzers, swept tune spectrum analyzers versus fast Fourier transform analyzers versus devices like these where we're just capturing the bins and reconstructing those in different ways. So that's all part of that other paper as well. But good catch, John. Thank you. All right, now I'm nervous because John's listening, and if I get any of this wrong, he's going to tell me about it. All right, so Heckle point number 2 goes to Downey again. Okay, so the same, periodic, sinusoidal, different shapes. They're all large waves. So regardless of how close together the peaks are, or how many there are, these are what we would call a simple or a periodic sinusoidal standing wave. And they're represented a bunch of different ways, depending on the nature of the impairment, the size of the cavity, and how much energy is being reflected. So now we can talk about compound standing waves. And as we mentioned, most of our examples just include one reflective cavity, meaning you have one reflector on either end and that cavity size is fixed. Now imagine that you have a span of trunk cable, trunk spacing that's maybe 1,800 feet, okay? Now amplifiers and the connectors on the ends can be pretty natural reflectors. Now let's say out of that 1,800 feet, 600 feet away, you have a radial crack, okay? Now that also becomes a reflector. So in that total cavity, now you've got your initial reflector, which could be the output of your amplifier, your radial crack, which is at 600 feet, and then the second reflector could be the input of the next amp with a loose or corroded connector. Now you actually have 3 cavities, right? You have the full one at 1,800 feet, you have one at 600 feet, and you have one at 1,200 feet. So now there's multiple cavities that have energy bouncing back and forth, different groups of reflections, and all of that energy is being reflected in different ways to create a compound standing wave. Now you can throw other things in there and put some water in that cable that got in through the radial crack and settled in the cable and created attenuation nulls that will identify as what we call water waves. So these are standing waves that are not periodic or purely periodic like the previous ones that we looked at, right? So the peak-to-peak differences are products of your multiple reflective cavities and the energy being bounced back and forth. So now this doesn't immediately tell you like how big your cavity is, right? You have to go to your intelligence tools and it'll probably show you a couple of different cavities. However, when you look at the response itself, you can say, hey, I have more than one thing going on, right? Where before, when I look at the periodic sinusoidal wave, I can look at that and say, there's likely one primary problem here that's creating this big cavity because it's periodic. When I look at a compound standing wave, I'm looking for multiple sources that are combined together. Okay? Now, water waves are